Welcome back. I know it's very, very distracting to have so much coffee and food and conversation outside, but we have a wonderful session coming up now on missions. So we've got 6 speakers. If there's time, we'll have 1 or 2 quick questions after their talks, and then we have a short panel discussion as well with 3 of them afterwards. Now, I can see a wonderful front row in front of me, directly in front of me, and because the lights are quite strong, I can't see much beyond the front row, and therefore, for our wonderful speakers, please can I encourage anybody coming in or anybody in the audience who wants even a better view, come and sit in the front row. Thank you so much, Jim. Thank you very much. Please join Jim on the front row. Oh, wonderful, wonderful. It is really lovely to have people, at least human bodies, in the front row. Thank you very much. So, as I said, this session is now on missions, and first up we have our very own, all the way from Strassen in Luxembourg, Abbie Hutty, who is the lead systems engineer for iSpace Europe, and she's going to talk about Magpie.
Hi, it's good to be with you all today. I'm just going to put the microphones into Hobbit mode. So my name's Abbie, and I'm the lead systems engineer for iSpace. I've been with them for about 5 years now, and I'm going to talk to you about our latest rover mission that we're building, which you've heard alluded to by some of the esteemed guests that introduced us this morning. We heard from Bob. Thank you very much, Bob, for name-dropping us. And we also heard from Andreas, so thank you as well. So, Magpie is a rover mission that's being built right here in Luxembourg. And we proposed this several years ago as part of ESA's SMEX program, so the Small Missions for Exploration. Now, this is ESA trying to do things a bit differently, trying to embrace new space and all that can offer the space industry and the institutional missions by approaching things in a slightly different way. And we're very proud to be one of the first SMEX missions to be going forward. We wanted to share this slide, although I think Andreas showed a slightly more updated one when he gave his talk earlier. And this is all of the European Space Agency's supported missions to the moon in the forthcoming years. And you'll notice just at the bottom of the moon here, Magpie in 2029. This is our rover mission. So we're very excited that we're going to be able to have this mission as part of the SMEX program, because SMEX allows us to bid a mission. So iSpace put together this mission from the science concept through the consortium, right the way through to the actual implementation and operation of the project. And that's quite a new concept for ESA. In their science missions, generally speaking, ESA comes up with the science objective, writes the requirements, will maybe have different phases of the mission that will be bid for by industry, and then we'll pick the final industrial prime, put together consortium, maybe manage the development of the payloads to be on the mission, and then we'll operate the mission as well. For Magpie, iSpace is taking basically all of those roles. So we have defined the science objectives for the mission. We've put together the consortium among industry partners that we've worked with in the past, and we have come up with the science mission based on... Keeps coming. We've put together the science mission based on capability. So we're really trying to do things in a very different way. Rather than having a grand science ambition and saying, this is what we want to do on the moon, how are we going to achieve this? What instruments would we need to take? We've started from the other end and we've said, what have we got? What works? What have we proven in other missions? And we've put together a consortium of European players that really have experience, that really have instruments that already work, that have capability that's already proven. And we've put together a science mission that combines all of these capabilities. We've worked out what we can achieve during the mission lifetime, and we've put this as a package together to ESA and said, this is what we can do with our mission, this is what we can achieve with our mission, and this is the price that we can do it for. And that price is a fraction of the price of a conventional ESA science mission. And I think that's why it's gained so much traction. So this is really the first time that ESA has tried to especially have a surface mission in this way. And as it stands, we stand to be the first ESA exploration mission on the surface of the moon, the first ESA-supported rover mission to the moon, and if we're successful in our science ambitions, the first in-situ water detection on the moon, all of which would be accomplishments that we'd be very proud to claim. We've put this together on the basis of our existing heritage, not just for the consortium, but with an iSpace as well. So iSpace, as you may have heard earlier in some of the talks, put together the first European-built rover and launched it to the moon back in 2025. Now, this rover was a lot smaller, about a 5-kilo rover, and we proved through that mission the design, the build, the testing, and the operation of that rover during the transit to the moon, that we have really got all of the capabilities right here in Europe and right here in Luxembourg to do these things. We've also demonstrated the space law that we need to be able to have this mission go into space. And so this whole end-to-end package is what we've managed to present to ESA as our proven capability. So here you see our team in Luxembourg. We're very proud to be a very diverse and international team. We have about 50 members of staff, and we have about 35 nationalities among those members of staff. And together we have designed, built, tested, and operated this rover, all from Luxembourg. We've also got a bit of a first in terms of the science for MAGPIE. So the principal investigator for MAGPIE is an iSpace member of staff. She's our chief lunar scientist. And so she's been putting together, and now with a team that we've expanded, to define what our mission objectives should be, define what our science goals can be, design our science requirements, flow down from that our different payload requirements, our subsystem requirements, and make sure that we can have a mission that completely closes, that achieves these meaningful science objectives that really do add to the European as well as the global science understanding on the moon. You can also see our operations team here. So when the rover is launched, we operate it exclusively from Luxembourg, and we have the full rover operation team based here 24/7, commanding the rover, controlling the rover, getting the science back and making the decisions about how to progress in the next phases of the mission. We've got a European consortium where we're putting instruments from lots of different places all together on this mission to really develop that pipeline and to diversify the capabilities within the European ecosystem to be able to work on future lunar missions, do future ISRU, and to keep going as we go into the future with larger rovers, grander missions, and more ambitious science. So to just give you a really quick introduction to each of those instruments that we have on board, we start with SENSE, who's providing lunar RIMFAX. This is actually a rebuild of the RIMFAX that flew already to Mars and has been operating there successfully on Perseverance. So this is a ground-penetrating radar. It can scan underneath the lunar surface and detect the different layers in the regolith and tell us a lot about where there could or couldn't be water ice deposits, different deposits, what those processes were, geologically speaking, that have created the topology that we're seeing there on the surface. We've then got an instrumented drill, which is called LVS, the combined instrument. So this is made of 3 separate components. We have from TUM I believe Philip is going to be talking later in the week, and you can hear from him then. The drill head itself, which will be able to drill into the lunar surface. It has a heated rod that will evolve volatiles from the lunar surface and trap those volatiles within the drill bore itself, which will then pass through a pipe and onto the ion trap mass spectrometer, which is being provided by the Open University in the UK. And that will be able to tell us what those volatiles are comprised of, whether we have water ice, whether we have other volatiles there, whether they're organic in nature, other things like that. And then we have, also from the UK, from ESR, a translation unit, which is the mechanism responsible for moving the drill up and down so that it can penetrate the lunar surface. Then we also have on board from the Czech IEAP, hard picks, which they've flown several hard picks already to low Earth orbit, to the International Space Station, but this will be the first hard picks on the lunar surface. We actually have 3. So we have a standard hard picks, which is a radiation detector on the lander itself, and then we have 2 hard picks that have a special conversion coating on their detector, which only allows neutrons to pass through, so that we can determine how many neutrons, what the concentration of neutrons coming back from the reflected radiation in the lunar surface is, and that will give us an indication of the subsurface hydrogen content in the area where the rover's standing. So with all of these instruments, we have a pretty good science suite to be able to tell you about the topology, the geography, the geology of the lunar surface, but also a lot about the lunar subsurface, the regolith composition, the volatiles content, and so on. And with the subsurface hydrogen in the picture, really telling us a lot more about the water and allowing us to prospect for that on the surface. So that's my time, very much at a close, but I really look forward to anyone coming to talk to me that's interested in hearing more about MAGPIE and more about iSpace's missions in Luxembourg and globally as well. Thank you very much.
Thank you so much to Abbie, and she will be on the panel a little bit later, so you can ask her some questions then. Next up, we have Edgar Milic, who is from GomSpace and is going to talk about nanosatellites. Welcome, Edgar.
Thanks, Lisa. Thanks, everybody, for being here. My name is Edgar Milic. I'm Vice President for Advanced Mission at GomSpace and Managing Director of GomSpace Luxembourg. As most of you know, GomSpace is a company with headquarters in Denmark, but with a large presence here in Luxembourg since almost 10 years, and mostly dedicated to space systems, particularly nanosatellites and microsatellites, but expanding. In order to start on this topic, let me take the clock back 2 centuries. In 1804, Meriwether Lewis and William Clark embarked on what was called afterwards the Lewis and Clark expedition, which was commissioned by President Jefferson to explore North America. The objective was to map, to find new tracks, and to find new resources. The results of that expedition 200 years ago shaped, of course, communications, shaped roads, which are still used today, and shaped businesses after that. Today, as we all know, we are on a journey which is aiming at mapping an area which is 4 times that territory, and is an area which is far, far away. What we know about the moon today is that it is far from the lifeless rock that we have been thinking for a long time. Also, after the Apollo missions, the idea was that there was not much and it was not worth going back. But I think also with the Apollo missions and also with the additional data that have been recently uncovered, we now know there is actually rich in resources. And of course, we are talking metals. We are talking the probable presence in higher abundance of helium-3, and of course, water ice at the poles. And waterize, as we know, does not mean only life sustainability, but it means that you can produce fuel if you are there. Now, what we are lacking today is precision. So it's the ability to identify that a certain amount of resources of a certain kind are not 100, 200, 300 kilometers away, but are 10 kilometers away or 20 kilometers away. And therefore, they can be reached by rovers, as the one that we have been hearing about also in the last presentation. And that's where the Oasis 1 mission comes into play. The mission purpose is to have high-definition maps of resources on the moon. And that means water ice, that means metals, that means helium-3, that means rare earth elements. In order to achieve not only scientific discoveries, but actually to create maps, high-resolution maps, that can trigger new business models, that can make real the possibility of exploiting resources coming from the moon. Therefore, there is a scientific, but at the same time, a very much business-oriented goals. The concept is to fly very low on the moon's surface. We will have 2 orbiters flying around the moon, and they will be taking pictures at a very high resolution and taking measurements at a very high resolution, therefore permitting to have this mapping that makes a difference between you being very close or far away from a certain amount of resources. GomSpace Luxembourg specifically, is in charge of the platform and the satellites. We leverage our heritage, and I will talk about that also in the coming slides. We leverage our heritage, which is largely coming from another Luxembourg mission, which was the Juventus, which is still today the Juventus mission, currently flying to the Didymos asteroid system. It's going to be 2 12U satellites with 4U in payload size, with 4U propulsion unit. We need to have quite significant propulsion in order to be able to fly very low on the surface of the moon, above the surface of the moon, and 4U for the avionics. As I said, there is a clear legacy that we're using for this one. And that's the one associated to the Juventus, or Hera, if you want, mission. Hera is a mission which was launched end of 2024, on October 7th, which is going to arrive at the Didymos asteroid system at the end of this year. There is a very important Luxembourg component on board of that satellite, and it's a Juventus nanosatellite, a 6U nanosatellite, which was conceived and engineered here in Luxembourg. The system, the spacecraft as a whole, is going to visit the system that was, as you may remember, in 2022, was also visited, and Dimorphos, one of the 2 asteroids, was hit by DART. What Hera is doing is going to go and check what has been the result of that, and particularly Juventus is going to look below the surface. In that sense, Juventus is a milestone in deep space missions. And it has a very important role for us versus the Oasis 1 mission, because it permits us to have tested systems, to have operational experience with this kind of missions, and to have the possibility of having lessons learned and knowing what to avoid and what to leverage even further. All in all, that brings a significant advantage to the Oasis 1 mission, which is reduce risk and accelerated development in order to stay within the budget and in order to meet the very challenging milestone of seeing the system launched at the end, towards the end of 2027. Operationally, Oasis 1 is going to be a bit different than what you see here, which was a part of the Hera and Juventus ConOps. But there will be significant similitudes as well. Of course, we will be hosted on board of the Mk1 from Blue Origin, and we will be detached in the same way that that is going to be for Hera. There are still trade-offs in terms of how we will stay connected with the main spacecraft. If we're going to have an umbilical, for example, this is still an open point. But after we are deployed in the same way that we are talking for Hera, then the satellite will be free to go and will start all the actions needed to deploy the systems, solar panel, testing the payloads, and then being ready to operate the mission. The heritage is not only the one of Juventas. The heritage goes back 20 years. GomSpace has been doing nanosatellites in 1U, 3U, 6U, 12U, and all the U's that you want, up to the microsatellites that we do today, for 20 years. That has permitted to accumulate a very significant flight heritage on all the subsystems which are inside the spacecraft that we fly today in LEO, but also in deep space. All those subsystems are the ones that recompacted together, rearranged, and used in other forms, and evolved at times, of course, in order to face a different environment, are going inside elements like a 12U satellites of the same kind that is going to fly on Oasis. For us, the 12U platforms is becoming a kind of soft spot. We are getting more convinced as we go through the development, and we are at the moment in PDR stage in the mission. It's becoming a soft spot, a kind of small, smart, lunar-ready platform that we have. We are using that in other formats also for our LEO customers, for the many LEO customers that we have. We can have up to 9U in space for payloads in LEO, while, of course, in the case of Oasis, as I said, there is only 4U left, which is in any case more than enough in order to accommodate the spectrometer and the magnetometer that we have on Oasis. Now, the story of this project is also a story of an exciting partnership. Blue Origin and GomSpace come together from different perspectives, from different trajectory, but they both share a spirit of innovation and of daring and of taking the objective far beyond the normal limit of imagination. We have worked together for a long time, even before the kickoff that we had at the beginning of the year. We have worked on this one for some years already. And always with a spirit of looking at things and challenges together, because you always have challenges in this kind of mission. But the difference is made by the way that you approach the challenges and you solve them together. All in all, the result is a partnership at the basis of the mission Oasis, which is bringing new low-cost lunar access, fast iteration, enabling new business models, and even more importantly, is another sign of what Luxembourg can lead in the activities related to moon exploration and resources prospecting. And this is done by two companies which are present here in Luxembourg. GomSpace since almost 10 years, and Blue Origin, as you may know, very recently. Thank you.
Thank you so much, Edgar. Now we have a talk from Mtronics. Please welcome Christian Schmidt, who is the Advanced Radar Instruments for Near-Earth Asteroid Characterization. That's what you're going to talk about, Christian, so welcome to the stage.
Thank you for the introduction. Right. My name is Christian Schmidt, RF engineer at Mtronics. I'm going to talk about our recent and current activities in planetary defense, but in that sense also regarding space resources, which is, in my opinion, a linked topic in some regard. I'm going to give a brief overview about these missions and go into detail of about two of them. One we just heard before from Edgar Milic, the Hera spacecraft and Juventas CubeSat. Then over to Ramses and a bit an outlook from our point of view. For the Hera spacecraft, or for the Juventus CubeSat, in fact, we were the main contributor with the low-frequency radar called Jura, Juventus radar. As said just in the talk before, launched in 2024 with destination Didymos binary asteroid system, with the goal to do radar tomography and material characterization of Dimorphos, which then is also linked to space resources, because first of all you need to know what kind of material properties you find, and you want to possibly then harvest. The cruise phase commissioning so far for our instrument is absolutely nominal, so we're happily alive cruising through space. Based on this, we also contribute now to the next planetary defense mission, which is Ramses, with ARA, the LFR for that mission, which is an adaptation of the Jura design to the new mission specifics, but in essence it's a lot of reuse, and it's also a lot of reuse that speeds up this process, something we heard also in the talks before. It's about gaining experience and thereby also accelerating what we're doing, what we want to achieve. The destination here is Apophis. You might have heard of that asteroid, which will encounter Earth, or which will have a near-Earth flyby on 13th of April 2029. Perhaps someone knows why I underlined the 13 in the date. Can't see you, but for anyone who doesn't know, it's a Friday. So Friday 13th, we'll have this flyby at around, I think it's 35,000 kilometers, which is really quite close. Which is also a good reason to do the planetary defense missions. The same goal a bit here, radar tomography, with the specialty that, of course, during flyby, some effects on this small body is expected, and also this will be part of the characterization we're doing, together, of course, with the consortium. In this case, I mentioned it before, Juventus was flown on a GOM-Space platform, Jura was flown on a GOM-Space platform. In this case, it's a CubeSat from Taiwan in Italy, which also shows the collaboration across Europe for these missions. For Ramses, we just recently passed the CDR. Qualification of the PFM models will be end of this year, and then delivery to Taiwan for integration. Briefly for the instrument itself, and for anyone who's perhaps a bit deeper into radio frequency, it's a low-frequency ground-penetrating monostatic synthetic aperture radar. It's quite a mouthful. At 60 megahertz center frequency and 20 megahertz bandwidth, to characterize the outer surface, but also, as far as possible, the interior, really, of the asteroid, to get an idea of the materials, but also the material properties, but also the structure itself, whether it's a rubber pile, a solid rock, something in between. Well, it's BPSK coded for anyone who's interested. We can also have a chat about that later. And then, also very important, the two antenna pairs that are, of course, part of this radar. So on the right-hand side, you see the actual PFM model that's currently flying. And the two antennas, or two such antennas, that in the end transmit and receive the radar signal. For this, I need to turn a bit because it's quite a lot. First of all, it's a multinational consortium across Europe. So Mtronics in Luxembourg for the Jura instrument was responsible for the project management, the system engineering, the actual SDR platform, which was then an enabler for our partners to build their specific radio frequency front end that fits the actual needs, also in terms of science requirements, of course. The main software, mechanics, testing, and qualification, all of that was done here in Luxembourg by Mtronics. But of course, specific parts of the whole instrument were done by contributors like Filip Zaplata, now as a company, FSATCOM from Czech Republic, who did the main low-frequency radar IP core, so the actual firmware in FPGA that's doing the signal coding, the signal modulation, demodulation, and so on. Then, most importantly, I could say the Institut de Planétologie et d'Astrophysique, IPAC in France, in Grenoble, with the scientific lead, Alain Henrique, that's the scientific lead and the main instrument design from a science point of view. In addition, they also designed the actual receiver board that's then hosted inside, on top of our SDR platform. Likewise, we have the Technische Universität in Dresden, TUD, Germany, that designed the transmit board for the power amplification, the switching matrix, and so on. And the antenna design, and finally Astronica, company from Poland who designed and manufactured the actual deployable antennas that you've seen just before. Going quickly through this, currently we are today, I can say we are at a distance of 185 million kilometers from Earth, meaning if you look on the picture on the right, on your right exactly, the white spots you see there, that's the actual Hera spacecraft. The green dot, that's Earth. So we made one turn almost around the solar system to arrive there end of this year. There's some work in progress, of course, as I would say usually in such projects. In this case, it's the antenna deployment procedure which had to be a bit changed from the initial planning. I guess that's life, but we still have some time until arrival. Moving on quickly to Ramses, they're a bit the same approach, but like I said, it's even shorter development time because we have a lot of reuse from missions before, but it's a unique science opportunity to have an asteroid that flies by that closely. Again, we have a multinational consortium. This time it's led by TAIVAC, Italy, and all the parties you've seen before are now contributing in this direction, but kind of the same setup. The full instrument design is reused with some thermal optimization, of course, the different mission profiles, the different platform, the data interface and antenna interface has been optimized, but also really just adapted to a different CubeSat platform. And then a bit of outlook to future mission opportunities, let's say, from our side, from our point of view, based on a new product, off-the-shelf product development from our side, a new generation SDR platform. We had an internal case study for bistatic low-frequency radar, something already discussed in the past, also in the context of the Jura instrument, where Alain Henrique, for example, he had a bistatic radar, so radar where transmitter and receiver are apart from each other, flown on the Rosetta mission. This is something where we have worked on an internal case study, and for anyone who's interested in this, we're also searching for collaboration in this direction, which then is, of course, also something, a good showcase for our new product that you can see here, an off-the-shelf SDR, software-defined radio with 6 RX channels, quite high-performant clocking system, so ultra-low phase noise, meaning improved performance in the end and enabling these future missions, especially for timing critical, like it is the the case for biostatic radar. And with this, I'm at the end of my talk. I thank you very much.
Thank you, Christian. And next we have Gary Lai, who's come to talk about Interloon, commercial-led missions to prospect the moon for helium-3. Thank you, Gary.
Thank you, everyone. It's great to be back here in Luxembourg. I spoke here last year. It's actually my third year at this great conference, but I wanted to give you an update about Interloon, and in particular, the progress we've made on 2 upcoming lunar prospecting missions. So just a little bit, for those of you who might not know about Interloon, we are a company, venture-backed, US-based company, completely focused on space resources, initially helium-3, but not only helium-3. We have about 30 full-time staff so far, and our offices are primarily based in Seattle, Washington, where our main laboratory is, but we are also have an office focused on simulant development, a laboratory in Houston, Texas. We have so far had considerable support from the US government and various agencies, including NASA, which is a sponsor of 2 of our missions, as well as the US Department of Energy, the Rare Isotope Program, which rations all the helium-3 in the United States, the National Science Foundation, the US Air Force, as well as the Texas Space Commission. And a little bit different than before, something that has evolved at Interloon is we are not only focused on helium-3 now. We've realized over the course of the last couple of years that a lot of the infrastructure that is essential, that we will need to do helium-3 resource extraction simply does not exist today. So a broadening of the Interloon business plan includes development of some of that infrastructure for other uses. So we do a lot of hardware development. I have some pictures here of full-scale lunar excavator we built and tested, as well as helium distillation, 3 distillation systems. We've successfully shown that we can distill helium-3 from the regular helium supply on Earth, and at the concentrations that would be present on the moon, and a lot of beneficiation and comminution techniques with regolith. Helium-3, if you don't know, is an extremely rare and valuable resource on Earth. It is worth more than $20 million, and the current demand far outstrips the supply. The primary uses today are in border security and quantum computing, and we have already sold hundreds of millions of dollars worth of product in the form of offtake agreements with various customers. Our largest customer is in Finland, Blue Force. So we have more than enough demand for the product. The issue is getting it. A little bit of background on prospecting for helium-3 on the moon. It is present in high quantities on the moon. There is an estimated 1 million metric tons on the moon, but it is not possible to detect it by remote sensing from orbit. The only way to do it is with mass spectrometry, because it is at low concentration, and that is a direct measurement of a sample. But what we know about helium-3 concentration today is from the Apollo sample analysis primarily, where they showed a very strong correlation between the presence of titanium as well as maturity, and highly correlated linearly with helium-3 concentration. But you notice that relationship only goes out to about 15 parts per billion, and that is because they only went to the places on the moon that have that particular product of titanium and optical maturity. But from remote sensing data, there are places on the moon that if that linear relationship was present, there should be over 30 parts per billion. It should be, but of course, that must be proven, and that is the purpose of our prospecting missions. We have 2 in development right now. The first called Crescent Moon. The instrument for that has been delivered and is ready for integration and launch later this year. It was a collaboration with NASA Ames, as well as Astrolab, which has developed a flip rover. The picture of the instrument, which is called METAL, is there. It is a a reflectance spectrometer, which can measure basically the x-axis on that figure, the product of titanium and optical maturity. That should be a predictor for helium-3. It will go on the astrobotic flip rover on the Griffin lander, which is planned for launch later this year, and ride along the traverse of the rover, taking images and testing techniques to basically test for that proxy of helium-3 and mature our data pipeline. Then that will flow into Prospect Moon, the much more ambitious mission that we are working on, and that is to perform that direct correlation between the optical maturity and titanium, which can be measured with our metal camera as well as from orbit, and prove that the helium-3 exists at that concentration. So this mission will go to the highest predicted helium-3 concentration on the moon. It should be in excess of 30 parts per billion if the model is right, and prove that that relationship exists. I have an image from our design review of the CAD of the payload that is from our PDR that is then adapted to lunar environment. And so you can see every aspect of this payload is being developed by Interloon as well as direct partners of Interloon. It will consist of a 4 degree of freedom robotic arm that will be able to take samples of about 10 to 20 cubic centimeters and transfer them into one of 3 experiments. One experiment would perform size sorting on the regolith to get the fine particles. Another experiment is a pyrolysis experiment. It will heat the regolith sample to about 1,000 degrees Celsius. That should off-gas all the volatiles, which will then be measured by a quadrupole mass spectrometer. It will allow us to get not only helium-3 concentration, but all concentrations of all volatiles below 100 AMU. And then finally, we have a prototype device, mechanical processing device that we will use, that we intend to use in the larger scale system to prove that we can extract helium-3 without heating it to 1,000 degrees Celsius. And all 3 of those experiments that are mounted underneath the baseline lander are now funded, co-funded with NASA under a phase 3 SBIR, all the way through a production of the flight hardware by September of 2027. We are still working on the funding to launch it, but we have many potential funding mechanisms for that will follow soon. Beyond prospecting missions, Interloon does work on a lot of other things that might be of interest to you. So we have technologies for performing size sorting of regolith using centrifugal acceleration. We've tested that many times on lunar parabolic aircraft. We have mechanisms for doing that beneficiation and comminution of regolith. Also tested multiple times on lunar gravity aircraft, and that is applicable to any form of resource extraction. One of the largest areas of the company is to perform high-rate excavation and site preparation. And so in addition to our partnership with the Vermeer Corporation, we have a partnership with Astrolab, which is one of the prime companies under contract and in bidding to develop the new NASA lunar terrain vehicle. So with Astrolab, we have adapted our higher excavation and site preparation tools to the Astrolab Flex rover. And that is planned to be developed and tested in Houston, Texas. And then finally, just a little bit about the Interloon Research Lab in Houston. We are focused there on not producing bulk simulants, but producing specialty simulants. The very first simulant product we're developing is a simulant that is infused with solar wind volatiles through ion implantation. So that has many uses. The very first use will be to ensure that we can extract helium out of those kinds of samples, because of course getting actual lunar regolith that is infused with volatiles is very difficult. Our Interloon Research Lab also has close relationships through Space Act agreements with the NASA Johnson Space Center. So we view ourselves as a very, very easy way to work directly with NASA without necessarily going through the entire Space Act agreement process up front. And this lab is thanks to investment from the Texas Space Commission. So if you want to learn any more about Interloon and/or follow our progress on these very exciting prospective missions, please come to me afterwards. Thank you.
Thank you, Gary. And now we have Ben Bussey from Intuitive Machines, and he will also be on the panel discussion just after the next couple of talks. Ben.
Yep. Good afternoon. It's wonderful to be. Oh, I've got 8 seconds. Oh, I have to go. Wonderful to be here again in Luxembourg. Very excited to talk to you today. So, got lots of new stuff to talk about. The image on the right you've seen before, but the image on the left you won't. In fact, it's going to be very exciting. All the new stuff. In fact, the only thing old and tired is me. Right. So right now, through the company has expanded significantly, both organically and with acquisitions in the last year. So now we really have sort of 3 parts to the company. We build, and I'll give some more details of that, we build spacecraft and spacecraft systems. We connect those systems internally and back to Earth, and we operate those systems. So to talk about the build part, there's obviously the lunar lander side of the company is still a very integral. It's the heart of the company, and so IM-1 and IM-2 have now flown. We have IM-3, the Trinity spacecraft lander, will go to Rhina Gamma in late this year, and will drop off a lunar outpost rover. We'll explore that very interesting scientific area. We then have IM-4, which actually, you always find an error in your slides, which actually is going in 2027. That's also going to the South Polar region. That will carry a number of payloads, including the ESA Prospect payload. And then we were recently awarded our next lander contract with NASA. All 5 of these are CLPS, NASA Commercial Lunar Payload Services contracts. And so the 5th mission, IM-5, this is the first time that we will fly what we call a Nova-D, which is more of a cargo class lander. The Nova-D can take anywhere from 500 to 2,500 kilograms, and that will also go to the Mons Malapert region in 2030. We're also one of the 3 finalists for the Lunar Terrain Vehicle. IM-5 will carry RUVA, one of its payloads. We're one of the finalists for the Lunar Terrain Vehicle. You heard from Edgar this morning. There's been some very exciting changes with the NASA ignition, but that's still on the cards. Probably going to fly, sooner now. And we're also building 5 communication relay satellites. I'll talk more about those. The big change has been the acquisition of what was Lanteris Space Systems. Before that, it was Maxar Space Systems. So we've now drastically increased our ability to make satellites. We offer a full range. The IM-300 is a relatively small bus for Earth orbit. The IM-500 is a medium bus. Best example of that is the Worldview Legion satellites. There are 6 of those flying around the Earth, and they have they're very capable satellite, is acquiring data at about 34 centimeter resolution. And then we have the large bus, which is the 1300 class. This is a GTO scale bus. Some examples, there's about 100 of those right now in operation in Earth orbit. From a planetary exploration side, the Psyche mission to the Iron Asteroid, that is actually a 1300 bus. The power propulsion element for Gateway is a large 1300 bus, and as part of NASA Ignition, that has now been repurposed to a mission called SR-1, which will test nuclear propulsion to Mars. So our ability to build both landers and satellites has drastically changed in the last year. We're also developing, looking at nuclear space exploration in very much a variety of scales. At the low end, we're looking at an americium-based survive the night capability for the landers, all the way up to part of a team that's looking at potentially doing fission surface power on the moon, a key part of future infrastructure. On the networking side, so the middle one, networking or connect, there's two components to this. There's our ground segment. We do not rely on NASA's Deep Space Navigation System, which is only getting more and more overutilized for conducting our missions. We have contracts with radio science dishes all around the world, anything from 20 meters all the way up to the Parkes dish in Australia, which is 65 meters. So we use those dishes for ground link when we fly a lunar mission. We're also the first commercial company to demonstrate doing the ability to do orbital determination with our own ground stations and not having to rely on DSN. There's also the orbital segment to the in-space network. We won a NASA contract called Near Space Network Services, which will provide communication and precision navigation and timing for Artemis. But as has recently been the way with NASA, it's a commercial contract in the way that NASA is buying the service, but the way we implement it, the satellites will be IM satellites. And so we're putting up 5 communication relay satellites in lunar orbit. The first one is co-manifested with IM-3. It will launch at the end of the year. They'll be in elliptical orbit with hang time over the South Pole, but they will also be compatible with ESA's Moonlight program. We're also going to be putting science instruments on those communication relays to get new remote sensing, cislunar remote sensing data sets. And finally, we have the operate part of what the company does. So there's a range here. We have orbital transfer vehicles. So if we take a Nova C and take off the legs and the other landing systems, that essentially becomes a high delta V capable OTV. And we call that the Nebula. First one of those is flying in 2028. We also have the ability to host the payloads and do payload operation on the landers. Similarly, doing lunar mobility operations, which is hosting payloads on our vehicles, and also through another recent acquisition of a company called Kinetics that does the deep space navigation for a lot of the NASA missions. We now offer world-class expertise in navigation, flight dynamics, and operations. And Kinetics, the first private company qualified for NASA deep space navigation, and they've worked on some of the most complex exploration missions, including Messenger, New Horizons, and OSIRIS-REx. But finally, my favorite example of operations is, before I hit go, this is an image of the IM-2 Athena lander in orbit around the moon. We're fairly close to the South Pole when I hit go, and you'll see Shackleton Crater come up now on the left, about 20 kilometers, as we head over into the dark hemisphere. And you see lit mountains all the way, some of the places that receive the most illumination on the moon. One more time, because I didn't mean to do that. And thank you.
Thank you, Ben. I know that you're going to be back up for a panel discussion, so keep your questions for that for the panel discussion with Ben in just a few moments, right after a talk with Sotirios Zormpas from Lunar Outpost EU. So he's going to talk about high-fidelity lunar South Pole mapping to enable resource utilization and polar mobility. Sotirios.
Okay, thank you, Lisa, for the introduction. My name is Sotirios Zormpas, and I'm a Technology Development Manager at the European branch of Lunar Outpost, located here in Luxembourg. Today, I'm going to talk to you about how Lunar Outpost can enable resource utilization and polar mobility through high-fidelity lunar South Pole mapping, as already mentioned. For those of you that don't know much about Lunar Outpost, what we're doing is we are building the mobility, workforce, and infrastructure layers to enable human permanence in space. We do that through a hardware-first approach, as you can see from the high-fidelity model that we have developed here for NASA as part of the Lunar Terrain Vehicle Development Program. And a lot of times when we think about human permanence, we think about a lunar base. We heard today also about the plans for NASA on making a lunar base on the moon. So if we think a bit more about what elements will constitute that, we can see some of those here already. So we talk about prospecting and exploration, where mobility platforms will be able to seek out specific regions to understand the concentration of volatiles and identify key areas of interest within the landing site. We talk about autonomy and multi-agent collaboration, where different platforms will communicate with each other to perform tasks intelligently and faster. And also we talk about developing the infrastructure itself, as well as enabling human permanence through ISRU activities. A lot of times when we think about this image, we need to also understand how to get there. So breaking down the problem a bit into two simple aspects. One is landing accurately. That doesn't necessarily mean landing on a specific region on the moon, but that means doing so over and over reliably. The second aspect is long-term operation. This means that we need to increase the mission lifetime from lunar days, which is what most missions, what is the envelope for most missions that operate today, to months and potentially to years. So I'm going to talk to you about how Lunar Outpost enables those two aspects, starting with the landing accuracy. In order to understand the landing site, we need to gain knowledge on the topography. So we need to de-risk the landing site in order to understand what hazards exist for landers in the specific region that they want to reach. And we do that through Moonraker. Moonraker is a mission with a LiDAR that aims to map the surface of the moon. It will enable safe landing and transversal planning. Lunar Outpost EU is supporting NewView as the mission prime through the payload thermal design and model-based systems engineering services. And the point of the mission is first to perform high-resolution scanning to identify digital elevation maps of key regions on the surface of the moon. It does so by generating resolution up to 30 centimeters, which is far beyond the state-of-the-art of most data that we have to date. At the current stage, it is at the phase A, and it's funded by the European Space Agency with an expected launch in the second quarter of 2030. We foresee Moonraker to help a lot of those landers that we have heard from today, such as the Argonaut lander in the near future. Going back to this slide, we talked about the landing accuracy, but it's one thing landing on the moon, and it's another thing building and operating a lunar base. So in order to do that, you need robotic and crewed mobility assets. You need lunar night survival to increase the duration of the different payloads and assets, and also you need the infrastructure itself that will bring all those elements together. Through Lunar Outpost, we do that by providing mobility as a service. So last year we were able to land the first commercial rover on the south pole of the moon through the IM-2 mission. And now we are taking those lessons learned and integrate it into all our other missions. We are the only company right now, the only private company that has 5 contractual missions up to 2030. And you can see the cadence here almost every year. Our next mission is later this year with IM-3 that will go to Rainer Gamma, as was mentioned in the last presentation. But what the key takeaway from this slide is that we're not building only small robotic platforms such as the mobile autonomous prospecting platform, but we are increasing the capabilities of those platforms through small, medium, and also large human-rated vehicles such as the lunar terrain vehicles that astronauts would drive on the surface of the moon for NASA. And there will be a dedicated talk in this week by AJ, our CTO, and you can learn more about the LTV there. Our answer to lunar night survival is LUX Thermal. This is an autonomous infrastructure that is capable of providing heat and power on demand to different payloads and users on the surface of the moon. It does so by providing up to 100 watts of heat 55 watts of power, and maintaining a thermal enclosure, what we call a thermal garage, at a minimum of minus 20 degrees Celsius, which is the lowest temperature limit that most electronics can operate at. We have been building this infrastructure since 2023, and right now we are aiming to building a large thermal earth prototype, which will be tested at the beginning of next year at Esrig at the DTVC facility. The goal of all those efforts, of course, is for us to have the first commercial mission before 2030. The way that large thermal operates is through collecting the solar flux through a series of lenses and mirrors that you can see on the top left here, concentrating that into our thermal reservoir that you can see on the top right, where we store the heat into a phase change material that is heat up to 300 degrees Celsius, and we can store up to 50 kilowatt hours of energy. And you can see also that exact breadboard in our booth that is on the right here, so we can talk about that a bit later. At the same time, we are controlling the heat through thermal hardware that we're developing here in Luxembourg. One of those is our active thermal switch that has been part of our past and our next mission to the moon, and also with our own multi-layered insulation, our own MLI that we're also developing in Luxembourg, and it was aboard LEO satellite last month. The next step is to provide power. We do that by converting heat to electricity and provide power to customers that are enclosed inside our thermal garage, as well as to external customers through our external thermal and electrical interfaces of Lux Thermal. Finally, we are protecting those assets through hardware like the thermal cover, which is a deployable MLI that is able to protect assets from the lunar environment, such as from the lunar dust, and also maintaining the heat inside Lux Thermal. But in order to get Lux Thermal to the moon, we need to make sure that our thermal control is advanced sequentially to ensure a high probability of success. And we do that through this Earth-to-Moon maturation roadmap. The first step is TACOS. TACOS is an IOD-IOV payload mission funded by the European Commission. It stands for Thermal Architecture Components, and it encompasses a lot of the thermal hardware that we're developing here in Luxembourg and that we expect to operate in Lux Thermal. Some of those are presented here, the active thermal switch that I have already mentioned, thermal capacitor, and also our own MLI. And this payload is expected to launch in 2028. The next step is going around the moon. We do that through Moonraker, and in that sense, the thermal control of Moonraker will include our thermal capacitor that will be able to maintain the LiDAR at constant temperature during those periods of high heat dissipation when the LiDAR is active, and through our MLI that will be providing the thermal control in orbit as well as in transit. Of course, all of those different activities aim to get Lux Thermal on the surface of the moon, where this thermal hardware will enable to operate through multiple lunar nights. It will be able to buffer different heat loads from the high temperature region of our thermal reservoir all the way to the thermal garage of our customer. And our MLI and also our hardware as a whole will be able to extend its temperature limits up to 300 degrees. So if you have any questions for our thermal hardware or are interested in bringing your payloads to the moon, you can reach out to this information or come up to our booth, where we have also a great team that is comprised of mechanical, electrical, thermal, and optical engineers, and we'll be happy to take any questions that you might have. Thank you for your time.
Thank you. Thank you. You can stay on stage, actually, Sotirios. Actually, Sotirios, you can stay on stage, because everybody has been so brilliant about keeping into time. Sotirios, You can come back on stage. Because I'm going to actually call back all of our 6 speakers to take some questions from the floor, and then we can go into the panel discussion. So if we could welcome back all of the 6 speakers, and thank you, everybody. And then we can take some questions from the floor, and then we'll go into our panel discussions. So if I could see any hands, if you have any questions for our wonderful speakers. Yes, I can see a hand there. That's wonderful. There's the microphone coming to you right now. And introduce yourself as well. Thank you. It should turn on automatically.
Okay, good. So Robert Lindner from European Space Agency. Thank you very much, everybody, for the very nice presentations. I have a very specific questions to Ben concerning the nuclear power. You mentioned for RHUs the use of americium-241. Just for curiosity, where do you source it? Where do you get it from? Do you have already a concrete, let's say, production line or, let's say, contracts or anything in place?
I mean, we're aware of opportunities in both the UK and France for acquiring it. I can't say exactly where the source will be from.
That was a very, very concise answer. Thank you very much, Ben. Any further? Yes, we have a question. Yes, I think it's Jerry Sanders in the front row. Thank you.
Hi, Jerry Sanders Ezrick. I have a question for Edgar. So you talked about heritage hardware for the Oasis 1 mission. You also talked about flying low lunar orbit. The thermal environment for that mission is probably drastically different than your others, so I was curious how you were handling that thermal environment.
So at this moment in time, indeed, we are characterizing that, and we see that there is a need of some adaptation of the systems. I think that the major problems, not problems, but the major challenges that we had to find solution for are also in that area, but particularly in radiation. So that's the one that is actually even more challenging.
You don't have a lot of time to dissipate the heat between orbits.
Yeah. But that's so those are certainly challenges that the team, in any case, has already found solution for, considering the characterization.
Thank you very much. I know we've got 2 questions. If you can keep your hand up very, very high, we can get the microphone across to you very quickly. So we're starting with this question here, and then we have another. In fact, if you come close to the stage, I can help with microphones as well. So we'll take the question here first.
Hi. Do you hear me? Okay. Francesco Ladini, Italian Space Agency. A question for Abbie. Do you hear me? Okay, now yes. Francesco Ladini from Italian Space Agency. A question for Abbie. I don't know if you mentioned it, but who are you going to fly with McBride? I mean, who's going to be the lander? Abbie.
Sorry, that was a question for me.
Yes.
The lander.
Yeah, the lander for Magpie. Who's going to be?
The lander for Magpie.
Yes, so our lander, fairly predictably, is the ice-based lander. So we're flying with the Ultra lander developed in Japan.
Thank you.
Thank you.
Thank you. Jakub Ciążela, Polish Academy of Sciences and Mirror's company. I have a question to Gary Interlun about the mass spectrometer. And namely, who is provider of that, and what is current TRL of this spectrometer?
I got the first part. Who is providing the mass spectrometer? The second part I didn't hear.
Okay. TRL, what is technology readiness level at the moment?
Yeah, so the mass spectrometer is a new instrument, although it has heritage from other instruments, including MSOLO. We're working directly with Infocon to space qualify one of their commercial mass spectrometers. I'd say the TRL today on various components, is up to 7, but the rest of the instrument as a whole is a 5, and we're also developing a custom avionics suite for it.
Thank you very much.
Yeah.
I know, question right next to you. And then we have a question here, and another one over there. Clive Neal.
Clive Neal, University of Notre Dame. Question for Gary. Gary, your distillation process is
The microphones do work. You just have to be really close, very, very close.
Can you hear me now?
Yes, we can.
Okay. All right, question for Gary about the distillation process in 16G. Have you done, I see you doing parabolic flights. Were you able to test that to look at the efficiency in that lower gravity? Because I imagine gravity may have an effect.
Yeah, so far, unfortunately, on parabolic flights, you don't get enough hang time. Cryogenic distillation works on the scale of hours to weeks of time. You have to do a long exchange of gases between falling reflux and rising boil-off. So that is primarily by modeling. Certainly in 1G, we have tested the distillation process for weeks at a time.
I'm really enjoying this audience interaction. I think we had a question here first, and then we'll go to you.
Yes, Mel Gelderman for Space Age Ventures. To any of the lunar lander companies, are you planning to do any sintering of regolith for landing site preparation for landing pads? And what kind of performance do you think you can get out of like first generation landing pads with regards to weight class and how large will these pads need to be?
So right now, no, we don't feel a need for a landing pad. I think where that will come in is one of the exciting things with the NASA Ignition announcement and the idea you might have multiple landers needing to land close by, is we'll get a better understanding what the plume interaction is like, what is a safe distance to land. I think after we do that and start to land, say, 1 kilometer away from a previous lander and go and visit it and see what damage was done, that will provide sort of the information on what type of mechanism do we need. It could be a sintered landing pad, you could make blocks, it could just be a simple berm. I think one of the exciting things from having an increased cadence is going to be better understanding what that problem is.
Thank you, Ben.
Hi. Hello? Hi, I had a question for Interlume. Correct me if I'm wrong, you're trying to get helium-3 from the lunar regolith. Do you also get helium-4 at the same time? And if so, how do you plan to separate it?
Yes, we are trying to get helium-3 from regolith, and helium-4 is present. It's about 2,700 times, based on Apollo sample analysis, more helium-4 than helium-3, which is actually much higher concentration than terrestrial helium, which is millions of times more present helium-4. So that is where cryogenic distillation comes from. It's one of the reasons we're developing as a core technology. Basically, if you liquefy helium-4, the boiling point of helium-3 is even lower. So you will get a helium product at the top of a distillation column.
Thank you.
Hello, for Gary Lai as well again. You talked a little bit about how you guys are now focusing on mining other materials as well, along with helium-3. Can you talk about how that's changed the amount of time it takes for you guys to start profitably selling helium-3 and your margins as well? Because that understandably would add years to your development timeline, right?
Yeah, I mean, we have always had on our roadmap other resources that we're planning on doing. Among other things, the process of liberating helium-3 releases a lot of other volatiles, which we've always assumed were gases, like helium-4, for example, 2,700 times more helium-4. So I don't think it's really adapting or changing our roadmap for helium-3 at all. It's maybe moving up some of the phases of development that we had deferred to later.
Thank you. Yeah. We have a question. I've got so many questions. Who has the microphone? Somebody over here. Oh, okay, yes.
Hey, Matthias here. Question for Gary as well.
Very popular, Gary.
So how does the Blue Force agreement of 10,000 liters of helium-3 annually scale against your expected extraction capacity? Thank you.
I'm not sure I got the second half of that question. It was about the Blue Force agreement, I know that.
Yeah, that's correct. So how does the Blue Force agreement of 10,000 liters of helium-3 annually scale against your expected extraction capacity?
Yeah, so from the standpoint of both Blue Forest, Maybell, the Department of Energy, and other customers that we're negotiating with, right now we are sold out on all of our capacity for at least the first 5 years once we start planned lunar operations. So it's not a question of demand, it's a question of basically developing the system and getting there and starting to extract it. Now, we do have a terrestrial version of the supply chain now, as I mentioned. We are funded by the US Air Force. The US Air Force, which is US military, has a very high interest in helium-3 for quantum computing applications that have a very strong defense application. They are actually funding us to pull helium-3 from the terrestrial helium supply on Earth. We have an industrial partner, a helium plant operator, helping us doing that. So that is another way, because everything in space takes longer than you think. Terrestrial extraction is another way to meet all of our supply agreements.
Thank you, Gary. I know you have the mic. I'm just going to go behind you. Yes, thank you.
Hi, my name is Lainey. I'm from MIT. I also have a question for Gary. So my question is about your Crescent Moon mission, which I believe is going to the lunar South Pole. Can you talk a little bit about how you're choosing the specific locations to map for ilmenite? Because I think our understanding of ilmenite concentrations are primarily from the Apollo missions in the Mare region. So how are you going about choosing your specific areas to explore to map for ilmenite under uncertainty?
Yeah, so the Prospect Moon mission is not going to, the Crescent Moon mission is going to the South Pole. There's the rideshare mission on the Flip rover, which was already going there. The Prospect Moon mission, however, we will pick the landing site. We have to be a mid-latitude equatorial location. As you saw in those maps, those are the highest areas of ilmenite concentration. And currently we are doing that with very coarse maps on the order of 200 meter resolution scale from such as LRO and Clementine data. We would love for there to be higher resolution maps of ilmenite of TiO2 concentration. We would pay a very fair amount of money if those maps were available. And I know there are various companies and presentations working on that, and we are talking to some of them. Yep.
Question again?
So follow-up question, maybe even two.
We have to, sorry to interrupt you. The microphones are so sensitive, you literally have to be centimeters.
Now should be okay, right. Okay, so follow back, of course, to Gary, I don't need to say that.
This is the Gary show, actually.
So one follow-up question will be to the previous comment about ilmenite. Do you consider also M3 data on ilmenite? I know at least for some locations, there are probably slightly finer data from M3 mission than from Clementine mission.
I didn't quite get that mission name you were referring to.
M3, Moon Mineralogy Mapper. That is part of Chandrayaan 1, if I remember well.
I'm not personally familiar with that mission, so I can talk to you afterwards.
Yeah, it's also called M cubed. Clive says M3 or M cubed Moon Mineralogy Mapper mission.
Oh, okay. Yes,
instrument of Chandrayaan 1.
Yeah, we have not looked at that particular mission. We do have a proprietary model that is based on other mission data.
I will come up for my money if you start.
I'll talk to you later.
Okay, and another very quick then, extraction of helium-3 and helium-4, because that was commented as well. It requires very low temperatures, if I'm wrong. Correct me if I'm wrong, but I think it requires even close to 0 Kelvin. So if it's not feasible on the moon, do you consider to bring bulk helium to Earth and extract it on Earth?
Yeah, I mean, we do have a helium crisis on Earth. It's not that bad that the economics makes sense for it, at least now.
Thank you.
Thank you.
I know that Clive has a quick question, and I know there's a question at the back. So let's take this question first.
Hello. My question is for Mtronics.
Hooray!
Yeah, this is regarding the near-Earth asteroid characterization. I am interested to know if you have any contracts to use this data for mining purposes.
I think I didn't fully get you. You're asking if we are planning on using the data for mining purposes.
Exactly.
Have you got any contracts already?
Any contracts? No, because in this frame, in the frame of, for example, the Hera mission, the main goal is, of course, planetary defense, meaning our science team that we work with is focused on this. So from the overall programmatic stream, this is not foreseen. But I would say from our perspective, this is nothing we should rule out. So if there's interest, can discuss.
Thank you. We've got three more questions that I can see from the floor, and then I will invite my panelists to sit down, and then you can ask them more questions. So I know Clive has a question.
And this is not for Gary. Sotirios, you showed a very intriguing graphic in your talk about a rover building what I assume was a launch landing pad. And it comes back to the earlier question about launch and landing pads. And with NASA's ignition announcement, going back to the same place becomes really important with big landers. So you're going to need a launch landing pad. So is Lunar Outpost actually developing the robotic technology to actually create that? And are you allowed to tell us what that technology is?
I can answer the second part a bit easier. So I think we have a lot of capabilities and we have a lot of projects, and we have shown rovers actually building landing pads as part of our contracts. For more information, however, I would ask you to maybe defer that question to AJ in the panel that's coming up, so he will be able to share more.
Thank you. I know we have another question here.
Yes, another question for Ben from Intuitive Machines. Will the Micronova mini hopper be flying again on an upcoming mission? And what is the mission profile for this vehicle? And will it descend into one of the PSRs?
So it's certainly our hope to fly the Micronova hopper again. And yeah, it was designed for extreme access. So going into permanently shadowed regions was one of its mission profiles. Another was to go into one of the Mare lava pits and explore whether it's a lava tube or just a chasm underneath, or even just to get to the floor of deep craters very quickly, something perhaps where a rover can't do. So yeah, we are actively trying to pursue getting that flown again.
Thank you. Final question here before we then go to the panel.
This question is for Gary and Ben, so Intuitive Machines and Interloon. Gary, you mentioned in your presentation the Texas Space Commission and how you found great support and partnership within Texas. Is Florida part of your company's plans in terms of having similar support within the Florida space ecosystem? And I ask that as a Florida native.
I mean, Florida is one of the main centers of space development in the United States. There isn't a similar thing within Florida, like the Texas Space Commission, where they're directly funding grants for R&D development in the same way. But if one were offered, we would certainly consider it really anywhere. There are a lot of, not only in the United States, but around the world. Yes.
And I think you're asking Ben the same question.
I'll give you the same answer. But no, I think that Florida is one of those states that is very actively supporting its space ecosystem of small companies. Nothing quite on the scale of the Texas Space Commission, but we certainly monitor what's going on there.
Thank you very much to all of the questioners and to the panelists. I'm going to ask Abbie and Ben to stay on the stage for the panel discussion. Thank you, everybody else. And I'm also going, thank you.